Hello everyone. In this session, I am going to explain about effectiveness-NTU method for heat exchanger analysis. Now coming to overview of this session, first I will explain effectiveness of a heat exchanger. Then we will see number of transfer unit and capacity ratio. Then we will do derivation of effectiveness equation for parallel flow heat exchanger. Coming to effectiveness, what is effectiveness of a heat exchanger? It is the ratio of actual heat transfer to the maximum possible heat transfer. The notation is epsilon. It is the ratio of Q by Q maximum. Q is actual heat transfer. Q maximum is maximum possible heat transfer. So actual heat transfer rate in a heat exchanger can be determined from the energy balance equation on hot and cold fluids. That is MHCpH TH1 minus TH2 for hot fluid. For cold fluid, MCCpC Tc2 minus Tc1. The product of mass flow rate into specific heat is nothing but heat capacity of hot fluid, that is Ch. The product of MCCpC is nothing but Cc. Cc is capacity rate of the cold fluid or heat capacity of cold fluid. If Ch value is less than Cc, we designate Ch as C minimum. If Ch value is greater than Cc, then we designate Cc as C minimum. Now we will see what is the capacity ratio. Capacity ratio notation is capital C. It is the ratio of C minimum by C maximum. Number of transfer units NTU. It is nothing but UA by C minimum. U is overall heat transfer coefficient and A is the heat transfer area of the heat exchanger and C minimum is the minimum heat capacity rate between the two fluids. In order to find out effectiveness, we need Q maximum because it is a ratio of Q by Q maximum. So maximum possible heat transfer can be obtained with the maximum temperature difference in a heat exchanger. The maximum temperature difference is the difference between inlet temperatures of hot fluid and cold fluid. The maximum temperature difference is given by delta T max is equal to Th1 minus Tc1. A heat exchanger will reach its maximum possible temperature difference Th1 minus Tc1 when the cold fluid is heated to inlet temperature of hot fluid or the hot fluid is cooled to inlet temperature of cold fluid. Such conditions can be achieved in counterflow heat exchanger of infinite length. These conditions will not reach simultaneously unless the heat capacity rates of both fluids are equal, that is Ch is equal to Cc. When the heat capacity rates are not equal, one fluid having minimum value of heat capacity rate will experience maximum temperature difference. That is Q maximum is equal to C minimum into Th1 minus Tc1. So Q maximum is written as C minimum into Th1 minus Tc1. If Ch is C minimum, then Ch into Th1 minus Tc1. In some situation, Cc will be value minimum. At that situation, Cc into Th1 minus Tc1 will be the maximum possible heat transfer rate of a heat exchanger. Now we will see the effectiveness equation. It is already defined as Q by Q max Ch into Th1 minus Th2 divided by C minimum into Th1 minus Tc1. If you write for cold fluid, the actual heat transfer is Cc into Tc2 minus Tc1 divided by C minimum into Th1 minus Tc1. Now, if you consider Ch as C minimum, then C minimum get cancelled. The remaining equation is Th1 minus Th2 divided by Th1 minus Tc1. If you consider Cc as C minimum, then this equation becomes Tc2 minus Tc1 divided by Th1 minus Tc1 because Cc as C minimum get cancel each other. remaining equation is Tc2 minus Tc1, Th1 minus Tc1. Depending on the situation, you have to use respective equation. Now we will see the derivation part of effectiveness for a parallel flow heat exchanger. Before derivation, we have to do some assumptions. The assumptions are as follows. The overall heat transfer coefficient U is constant. Properties of fluids such as specific heat are also considered to be constant with the temperature. Heat exchanges takes place only between the two fluids and there is no loss of heat to the surroundings. That is, the perfect insulation of the heat exchanger is assumed. Then changes in potential energy and kinetic energies are negligible. Temperatures of both fluids remain constant over a given cross section of the heat exchanger. With these assumptions, we will start the derivation part. For that, you need to refer this diagram. Same diagram we have used for LMTD equation derivation. Delta T1 will be the difference between Th1 minus Tc1. Delta T2 will be the difference of Th2 minus Tc2. For the analysis purpose, we have used a small part of this heat exchanger, that area, elementary area. For this elementary area, heat transfer is delta Q. Temperature difference is Th minus Tc. Minus sign, negative sign is introduced because the temperature of the hot fluid goes on decreasing along the length of the heat exchanger. Now, total heat transfer rate equation based on overall heat transfer coefficient is written as UA delta Tm. If you write energy balance equation for hot fluid and cold fluid, you will get MHCpH dTh, MCCpC dTc. Negative sign because of temperature is decreasing along the length of the heat exchanger. Now, if you write dq for elementary area, for total it is q, for elementary area heat transfer rate is dq. Same equation we have written, u into Th minus Tc into A becomes dA for elementary area. So, from this equation if you write dTh and dTc minus dq by mHCpH and dTc equal to dq by mc into Cpc. Difference of dTh minus dTc is written here in this equation. Finally, we will get d of Th minus Tc divided by Th minus Tc is equal to minus u into 1 by mHCpH plus 1 by mc into Cpc into dA. This equation is only for small elementary area dA. For the whole area of the heat exchanger, we need to integrate. After integrating, we will get ln of Th2 minus Tc2 divided by Th1 minus Tc1 is equal to minus UA into 1 by mHCpH plus 1 by mCCpC. The simplification of above step is written here. Ln of same written minus UA by, they have taken mHCpH common outside. Then in this derivation, I have assumed CH value as C minimum. You can assume CC as C minimum also. Same equations we will get at the end. In this case, I am assuming CH as C minimum, that is the product of MH into CPH. I have taken outside as a common. 1 by MHCpH becomes 1 because it is a ratio of 1 by 1, it is 1. If you take MHCpH outside, remaining is 1 plus if you take MCCpC, MHCpH outside, you will get here it is C minimum by C maximum because CH you have taken outside, C minimum by CC, CC becomes C maximum. That is why this equation becomes C minimum by C maximum. Now, ln of base E it is, if you simplify this step, e power minus UA by C minimum into 1 plus C minimum by C max is the equation. Th2 minus Tc2 divided by Th1 minus Tc1, e power something is written as exponential, exp means exponential, e power of minus NTU NTU, because UA by C minimum value is nothing but NTU into 1 plus C minimum by C max. If you simplify above equation using this equation, because from this equation it is a effectiveness equation, if you take TH2 value and TC2 value from this equation, TH1 minus epsilon into C minimum by CH into TH1 minus TC1 will be the value of TH2 taken from this equation. If you substitute TC2 from this equation, epsilon into C minimum by Cc into Th1 minus Tc1 plus Tc1 divided by Th1 minus Tc1 is equal to same written here. RHS side remains same. Now after simplification, Th1 minus Tc1 minus epsilon into C minimum into Th1 minus Tc1 throughout common, remaining is 1 by Ch plus 1 by Cc. Remaining terms remain same. Th1 minus Tc1, Th1 minus Tc1, Th1 minus Tc1 throughout common, it get cancel each other. Now after simplifying, after cancelling Th1 minus Tc1 throughout, you will get 1 minus epsilon into C minimum into 1 by Ch plus 1 by Cc equal to exponential of minus NTU into 1 plus C minimum by C maximum. If you write this epsilon, nothing but effectiveness, from this equation you will get 1 minus exponential of minus NTU into 1 plus C minimum by C max divided by 1 plus C minimum by C max. You can assume CH greater than CC also, that is CC as C minimum. You will get same final expression for effectiveness equation. Note that same result would be obtained if we assume hot fluid as the minimum fluid as well as C minimum as a Cc also, where N is the NTU, C we have used here, that is the ratio of C minimum by C maximum. Here this equation, whatever the NTU is written as N, C minimum by C max written as C. That's it. Whatever the equations we have used in the heat exchanger chapter, which is available in the heat transfer data handbook by C.P. Kodandraman and Subramanian. We derived parallel flow counter flow equation LMTD, same equations available here. Then we have seen the correction factor, same equation available here, you can go through once. Then heat exchanger effectiveness, just now we have seen. Parallel flow equation, 1 minus exponential of minus N into 1 plus C divided by 1 plus C. With this, I am concluding this session. The following references are used for the preparation of these slides. Thank you.